Greetings TAs and professors. Today we will share our progress in the domain of recognizing emotions from EEG signals. Emotion recognition from EEG signals has broad implications. Imagine systems adapting to emotions, benefiting mental health, neuromarketing, and many more. Emotions are core to human experience, impacting well-being and interactions. Recognition can revolutionize mental health with early intervention and enhance personalized, intuitive human-computer interactions. In our exploration of emotion recognition from EEG signals, we drawn inspiration from prior research. Li and Liu achieved 93.5% accuracy in classifying happiness and sadness from EEG signals in 2009. Zheng and Liu demonstrated the potential of deep learning in affective modeling in 2015. Burt and several other authors achieved a remarkable 97.89% accuracy in emotion classification using EEG in 2019. Our project builds upon these findings. We're implementing a hybrid model that combines convolutional neural networks and long-term short-term memory networks to achieve high-precision emotion classification using EEG data. In conclusion, our motivation stems from the real-world significance of recognizing emotions from EEG signals. By building on prior work, we're contributing to the evolution of this exciting field.
Let me introduce our model, which is based on multi-layer perceptron, or MLP in short. MLP consists of fully connected linear layers that transform the input, and we use the ReLU activation function that adds the nonlinearity, and we apply dropout on the perceptrons for regularization and to prevent overfit. So why do we choose MLP? The first consideration is the input feature size. Our input have 2,548 features, which are the different brand signals at different timestamps. This is a relatively small number, and it allow us to have a reasonable number of parameters and model size, even we use the fully connected layers. So it is efficient in time and space. And the second consideration is its performance. MLP have a wide range of application, and its performance have been long proven. It can capture many kinds of possible relationships among the features themselves and also among the features and output. And as the structure is relatively simple, it is easy to train an MLP. Here's the structure of our model, which we call emotion net. And each block here is a layer of perceptron, and it can have an input layer that takes the brand signals as input, and an output layer that outputs the class probabilities. In each input layer and hidden layers, the ReLU activation is applied, and dropout is also applied for regulation. And we also show the input and output size of each layers here. In order to best evaluate the design of our model, we use the k-fold cross-validation method during our training. We divide the dataset into k-folds of equal size and train the model for k times. In each time, we'll train with k-1 number of folds. Then we validate the model with the remaining one fold. After this, we reset the model and prepare it for the next training with another fold as validation set. We repeat this process for k times, with each fold serves as the validation set once. The final performance of our model is the average across k trainings. In this way, our model is not evaluated on one random part of the data backlog, but evaluated comprehensively on the whole dataset.
For datasets, we first started off with the source file, emotion CSV, which contained the EEG signals with labels and indicating emotional state. And we went through the pre-processing using the standardization using standard scalar. And we splitted the dataset into training set and test set 80 to 20 ratio. And for our metrics, we used accuracy metrics and then the confusion matrix. For accuracy, we use it as a primary metrics for evaluation. On the graph on the bottom is our graph of average accuracy over epochs. And for the confusion matrix, we use it as a visualize the performance across the different classes. And for validation methods, we have two. One's k-fold, and we implemented the k-fold as a cross-validation using PyTorch to evaluate the model performance more robustly. And the other one is the holdout. It was our initial start off with the simple holdout methods for validation. We used the hardware of the Google Colab, which has the Intel Xenon CPU with 13 gigabytes of RAM and a Tesla K80 accelerator and 12 gigabytes of GDDR5 VRAM. And as a software, we used PyTorch, NumPy, SciPy, Scikit-learn, Pandas, and TensorFlow.
That's all for our presentation for the project Milestone. Thank you so much for watching.